So I want to start off our conversation about interpolation by defining what it is exactly we mean. Right? What is our goal here? So what we're going to do is we're going to start off with a set of points, x1, y1 through x sub n, y sub n. And our goal is to find a polynomial, p of x, such that p of x sub I equals y sub I for every I between 1 and n. In other words, each one of those points satisfies our polynomial. So here's how we're going to do this. First, we're going to start off with a simple case. Right? Let's say, just for now, that we only have 2 points. We're going to come up with a method for doing this, and then it'll be pretty easy to extend this to a larger data set. So what I'm going to do is I'm going to define these 2 new functions, L1 and L2. Right? And what I've done is I've taken x1 minus x2 and x2 minus x1 in the denominator. So the denominators are numbers, right? Because they're both based on known values. Then the numerators are x minus x2 and x minus x1. Now, here's why I picked those. Right, excuse me. Here's why Lagrange picked those. Right, we're deriving what's called a Lagrange polynomial here, which is why we use the L for our functions. So what I want you to do is, I want you to take these 4 functions and I want you to calculate these 4 function values. Right? You can pause the presentation here, work through those real quick, and then we'll talk about why those are significant. So hopefully you came up with these numbers, right? 1, 0, and 0 and 1. And here's how I'm going to use these to build up our final answer. Right? I'm going to take L1, multiply it by Y1, L2, multiply it by Y2, and add them together. Right? And on the right-hand side, I just wrote that out again, but with the formulas for L1 and L2. So here's how this works. Right? If we evaluate p of x at x1, this term goes away. As you saw up there in your calculations, right? L2 of x1 is 0. All that's left is the left-hand term, but that part evaluates to 1. Right? So all we're left with is 1 times y1 plus 0 times y2, which is y1, and that's what we wanted. Right? P of x1 is equal to y1. And if you do this again, right, you can go ahead and work this out on your own here. If you do that with x2, the reverse happens. The first term becomes 0. The second term's coefficient there becomes 1, and all you're left with is y2. So this polynomial, these 2 subfunctions, if you will, are giving us the result we needed by going away in different ways. Right? Sometimes they go away by going to 0 and they wipe out a term. Sometimes they go away by going to 1, which just leaves us with the y value that we wanted. All right. Now see if we can generalize this. So this is how we're going to define the nth Lagrange interpolating polynomial. And I know it looks a wee mess, right? And it kind of is, but it's not too hard to understand once you kind of dig down into it a little bit. First, you remember on the last slide we had L1 and L2, right? This k here is that parameter, right? So what we're doing in the numerator is we're taking x minus every x value except for x sub k, multiplying them together. And in the bottom, we're taking x sub k minus every x value, again, except for x sub k, and multiplying them together. That's what this bit here in the middle is doing. We've got k minus 1, k plus 1. K minus 1, k plus 1. That's why we need that weird little bit in the middle to say, okay, we're going to skip x sub k and do this pattern on the top and the bottom for everything else. Now, there is a somewhat easier way to write this. Some of you may not have seen this before. Everybody, I'm sure, has seen the sigma notation for writing the sum of a bunch of numbers based on a formula. This pi notation is the same thing, except it means multiply. Right, so this is saying that I go from 1 to n, figure out what each of those terms will be, multiply them together, and you get this subpolynomial. if you will. You notice that we do have this one little requirement down here that we do have to skip I equals k. Okay, once we've got those, we can do just like we did on the last slide. We're going to take L1 times Y1, L2 times Y2, all the way out to L sub n times Y sub n, add them together, and that is our nth Lagrange interpolating polynomial. All right, so that formula was a wee bit of a mess. Not the prettiest formula you're ever going to see. And especially when n starts to get even moderately big, it can get messy to use. Really the kind of thing maybe you'd rather program a computer to do for you. But in the next couple of slides, we are going to look at some examples, right? So you can see how we can apply this to find these Lagrange interpolating polynomials for some specific, reasonably small data sets. So that's what the links here are going to take you to. One of them takes you to the next example. The other one takes you to the next lecture. And if you like this presentation, please don't forget to click on the like button down there as well.